endogeneity that would otherwise be in the model. And once we've got a specification like that, the delta yt means it's difference. That means yt minus 1. Okay, that's what I mean by delta, the difference. We work with the differences to estimate, and that leads to what are called orthogonality conditions, and that leads to instruments which are orthogonal. But that means the instruments get consistent estimates of these parameters. Then we have to use instruments that are uncorrelated with the differenced errors. Therefore, this goes back to our Arlon and Bond. They say difference and then include instruments that are orthogonal to the errors, and therefore all instruments must be uncorrelated with the errors, and therefore you get legitimate, consistent estimates from doing that. But what we do is, because we've got spatial lag in our model, it's an extension of our Arlon and Bond, because we introduce spatial instruments as well. So spatial instruments are included. So in estimation, remember I said we've got these variables, that's the log of output differenced, and that's the log of capital differenced. And it's, to me, an unreasonable assumption to assume that they're exogenous. In other words, the assumption is, under exogeneity, that the regressors are uncorrelated with all past, present, and future errors. In other words, they're uncorrelated with the errors, which means they're uncorrelated with y, because y depends on the errors. So essentially, when you've got exogeneity, make the assumption of exogeneity, making really strong assumptions about uncorrelatedness between the drivers of employment and employment. Whereas in reality, employment would feed back and influence the drivers of employment. So we can make a kind of weaker assumption, say, well, they're predetermined, which basically says they're uncorrelated at time t, but are correlated at t minus 1 and earlier, and that's called predetermined. Or you can go the whole hog and make even weaker assumptions, which is what I want to make in this estimation, say they're endogenous, which means we've got this feedback going on, so that when you've got endogeneity, the regressors at time t are correlated with current and past errors. So in other words, output and capital at time t both affect and are affected by employment at time t, so we've got feedback. So that's the weakest assumption, probably the most reasonable assumption, that, you know, if employment changes, then it'll affect output. If output changes, it'll affect employment. You've got feedback going on. So we get endogeneity. So we need to allow our estimation to take that into account. Now, these are I won't go into great detail here, but these are the moments equations that are based on the assumption of endogeneity. And what you do basically is you lag sufficiently far back in time to allow these variables to be independent of the errors. That's essentially what you're doing. So you have to lag here, for example, you've got to lag by if t is 3, then you can only use time 1. If t is 4, you can use time 2. So what happens is, as time progresses, you can use more and more of them. They build up. So that determines, the ones you can use determines the instrument. Those are the instruments, and that determines the estimates you get. Whereas if you assume exogeneity, then at each time you can use all of them because they're always independent. So you get different estimates. So we're going to assume endogeneity of regressors and lag by 2 in time. These are what are called the orthogonality conditions. So if we lag the endogenous variables by 2 periods, we can use them as instruments. And we include spatial lags, and therefore we're extending the standard orthogonality conditions of our Arlon bond. So the estimation then goes in various stages. I'll skip through this quickly. We get the instruments, and that gives us consistent estimates of the parameters, gamma, rho 1, beta 1, beta 2. Once we've got the parameters, we can get residuals. Once we've got the residuals, we can then estimate rho 2 and nu I, and actually come to mu I as well. Once we've got the residuals, we can do this estimation, and then once we've got these estimates, we can go back and get our final estimates of these parameters of the model. So it's quite a complex procedure, but that's just a basic summary of what's going on. So we get consistent, we lag in sufficiently in time to get consistent instruments, get instruments that are independent of the residuals, get independent of the errors. From that, we get consistent residuals. From the residuals, we can estimate the parameters of this is a spatial moving average process, remember, and this is the correlation between the residuals, and then from that, we get our final estimates. I'll skip there. And these are the estimates we get. So I've not put down predetermined there because the predetermined are actually quite similar to the endogenous. But it makes a big difference. These are the variables, right? temporal lag, spatial lag, and our drivers. If we assume the drivers are exogenous, then we use different instruments. We don't have to lag so far back in time. And we get these parameter estimates, standard errors, t-ratios, which is parameter estimate divided by standard error gives you a t-ratio. And if your t-ratio is like above 2, roughly, then you're talking about something being significant. You know, well, obviously it's saying that we've got some very significant variables here, assuming exogeneity. Rho 2 is minus 0.41. That means, actually, because it's negative, because of the way I wrote down the equation, that means you've got positive spatial dependence in the errors as well. And these are the variances to do with the mu and the nu, which are the two components. Remember, mu is the individual heterogeneity effect that's constant over time. You want to pick that up because you're saying you want to allow for all these different unmeasurables that you've got in your model by this random error term. Now, if we assume endogeneity, we lag back in time further, then the parameters change quite a lot, and so do the standard errors. The t-ratio is all significant still. The rho 2 is smaller, but still positive, because it's negative there, that means it's still a positive effect. The parameters change quite a lot. Gamma is still the largest. Rho 1 becomes more important. The spillover effects are more important. Output becomes very small. The elasticity on output is very small. The elasticity on capital is actually slightly larger, but they're all significant. So there's a difference in the estimates that you get using different instruments. Okay. There are some conditions that have to be applied to assume stability and stationarity that I won't go into because time is passing. And the interpretation of the estimates. Now, looking at those estimates, that's misleading, actually. And this is one of the contributions, really, of the book by Jim Lesage and Pace, in that they emphasize the fact that the instruments you get, the estimates you get in that table I showed you there are misleading. They're not the true elasticities because we've got the spillover effect. So what you need to do is get the true derivatives. The derivative is not the coefficient because we need to take the spillover into account. Although, in the end, these are not that helpful when it comes to simulation, but it's worth mentioning that if you fit these models, you need to calculate the short run and longer run effects. These are the true derivatives, right? They're not the betas. You have to take into account the spillover effect as well. And there's this gives these short run effects gives the instantaneous response of employment to a 1% change at time t in regressor k in each nuts 2 region. So it's saying basically, in each region, if you increase like output by 1%, what is the effect on employment straight away, instantaneously? And these are the short run effects. And there's a direct, indirect, and total effect. So direct effect is the mean of the diagonal of that matrix, which you can calculate. Because you know all these things. You know, you've got your W matrix. We talked about how to get that from trade. We've estimated rho 1. We've estimated beta 1 and also beta 2. So we can actually calculate that and get the direct effect as the mean of the main diagonal, or the indirect effect is the mean of the off-diagonal, and the total effect is the sum of the direct and indirect effect. These are suggestions made by Lesage and Page as to how to summarize this complex set of data, actually, because what you're getting is here is quite a big matrix of quantities, and you want to summarize them by means. Those are the short-run effects. The long-run effects look like that. So the long-run effects are the outcomes if the change in the regressor is maintained ad infinitum. So you increase output by 1% in every region forever. Okay, so basically, you know, employment kind of builds up. The impact on employment builds up because you've got spillover effects going through time. So again, you've got direct, indirect, and total effects as the means of the bits of the matrix. So you get this kind of result, therefore. So this is beta 1, we estimated this. But when you look at the total short run, the most impressive one is total long run effect. That's like, what is the effect of a 1% change in output on employment? Well, you look at the model you estimate, it's only 0.028, but when you take into account the long run effect, in other words, holding that 1% consistent at 1% in every region over to infinity, it's like 1.89. Similarly for capital, it's 1.7. So even though the initial estimate looks very small, when you look at the total effects, particularly, then it looks quite large. But as I said, these are becoming standard approaches to how to interpret the parameters of this kind of model, this kind of dynamic model that you should look at. And it's a good summary in Paul Elhorst's book, actually. It's just come out in 2014. I suggest you look at that because he talks about this quite a lot. But in the end, it's not very useful. And I want to talk about a more useful approach. About another 10 minutes. So what we're interested in is not the very infinitely long time, but the medium term. And we want to look at what happens simultaneously when we change both capital and output. And we want extra flexibility to help us visualize what kind of policy will be required to enable EU regional employment to recover to pre-crisis levels. So we need a different but related methodology using prediction equations. Okay, that's a prediction equation. Even more weird than it. That is a weird equation even without all that, actually. I didn't realize it would look like that. But that's coming from some of the earlier literature on prediction. But actually, it's exactly the same as this. That's what it looks like assuming spatial autoregressive errors, which is a standard approach. This is what it looks like, the inverse there, and we've not got the inverse there. So we've got these two matrices, and this is with spatial moving average errors, which is the one we're going to look at. So we're going to use this kind of prediction equation. The G and N are based on the double. M is the matrix. I haven't mentioned M really, but M is, when we say we've got spatial moving average errors, we've got another weighting matrix to consider, and that's M. Now, actually, I've cheated a little bit and just used a contiguity matrix, just to allow spillovers locally for to mop up any other residual autocorrelation that we've got. Okay, so M is another matrix like W with similar properties. It's standardized, rows sum to 1. Okay. These are the parameters. So those come into this equation here. So I'm going to use these. Prediction, not easy. The long run is, I don't believe you can actually predict. Actually, philosophically, I don't believe you can predict. You can sort of do simulations and say what might happen, but the long run is truly unknown because the model parameters may not be stable. We're just assuming they're going to be stable in the future. Different variables may emerge that are currently dormant and unknown, and we need to forecast the regressors out of sample. In other words, do an ex-ante prediction. We need to say what's going to happen to capital and output in the future to say what's going to happen to employment using the prediction equation. Within sample, ex-post prediction is more feasible since the regressors are known and the dependent variables known, so you can actually make predictions and see how well they're doing by comparing it with the real data. That's what I'm going to do first. So there's my prediction equation. So I'm going to plug in these. I've got to carry over the top here to say these are all estimates. So because we know row 1, we can call it GN hat because we know row 1, gamma hat. We know everything here. We can predict log of employment because we know the log of output and log of capital into the future. We're going to use X post predict. We're going to predict when we don't need to predict. We know the outcomes, but this is just to test the model really. The other thing is that mu, which is the estimated individual effects. These are important. I've been banging on about using a panel approach. Well, proof of the pudding is we've got that mu in there that's picking up all the heterogeneity across regions. So what we do is we solve this recursively. So we start with time t, and then we get yt, and then we plug that in and do it through time to get these predictions. Okay, so it's recursive, a recursive process. We use the observations for the first time because we don't know anything, and then we predict for the next time, and then use that prediction at the next time as t-1 to predict for the next time, and use that one as t-1 to predict for the next time through time. So recursive estimation. Mu1, we don't really know. These are the individual effects. So I'm just going to estimate those using the residuals. So I'm going to look at the residuals and say, well, we're going to... And that's how I'm going to do it. I can't go into that in great detail. I just start off with the equation, get the residuals, and then you can manipulate that to get the mu's, get the individual effects. But I haven't got time really to go into how to do it in detail. It's a simple procedure of working with the residuals to extract the individual effects. And that's four-step prediction, actually, 4 steps ahead. So, I mean, I must admit my data's a bit out of date, but I can predict. I've got data up to 2011, because there's a lot of work involved in getting this data together. So, but this is predicting 2008, 9, 10, and 11, 4 steps. Okay, so you see that's not too bad in terms of how the thing's performing. And this is like taking a snapshot. This is what actually the level of log level of employment at 2000 across the 255 NUTS2 regions. We're down here somewhere, just there. And this is the prediction. It looks pretty similar to me. It's not exactly the same. You look at the distribution, so there's a slight, but it's very, very similar in terms of the actual employment levels in 2008 versus predicted employment levels in 2008. So that's just one of the 4 steps ahead, just to give you a snapshot as to what it looks like. Ex-ante prediction, this is really saying, well, actually, no, we want to predict actually into the future on some assumptions about the levels of the drivers of employment. So we've got our other parameters, but now we need to say what the assumed levels of log output and log capital are in the future. And I'm going to take two scenarios. One is austerity, and the other is boom. So in austerity, I'm going to say, well, what would happen to employment if growth of output and capital over the period 2012 to 2020 was the same as in the early years of the crisis, equal to the EU regional means of 2007 to 11? So that means that I'm going to assume that there's minus 0.5% growth per annum of output and minus 5% per annum for capital. So I'm going to say take 2007 to 11 and use these numbers and into the future as to tell me what the levels of output and capital will be into the future. So it's assuming austerity, nothing, things stay really bad, and we want to predict what the outcome will be for employment on that basis. The other is the boom scenario. So I'm saying, well, what would happen to employment if growth could recover so that the drivers of employment grew at the pre-crisis rates of 2000? So I'm taking the 1997 to 2007 averages across the NUTS2 regions, 2.7% and 3%, and I'm going to grow it into the future. So I'm saying, well, growth continues at austerity until 2015, then assumes that the economy reverts to the pre-crisis growth rates from 2015 onwards. So we get, like, all of a sudden a boom occurs, like pre-2007, and what happens to employment then? So these are different scenarios. So this is the austerity scenario. That's output, and that's the boom scenario. So it's growing at the pre-crisis rate there, and that one's continuing downwards. And this is for capital. So that's a boom scenario and austerity scenario there. So I'm assuming that and applying those growth rates to each region, and then seeing what the outcome is. And that's the outcome under austerity for 2000. What I've got here is a map of the difference between log of employment in 2020, the prediction, and the actual log of employment in 2007. And you can see basically under austerity, things look quite bad because the difference is negative up to 10% and 20% less than the peak year of 2007. There's a couple of regions, sort of rogue regions, that happen to get away with it and grow faster, but essentially, and it looks pretty bad, particularly Spain, Ireland, and Greece. And most regions are this blue, light blue colour. There's over 110 regions or thereabouts which are have got less than zero. So employment is really hit hard by this austerity scenario projection. What happens under the boom scenario? Well, things look pretty good in that here's the distribution. So even the worst regions like Greece and Ireland and a couple of English regions have caught up to the 2007 peak. In fact, some regions are 10% above the 2007 peak in employment. Some even 15% above. So we get a recovery of employment. So essentially, the point I want to make here is that the recovery is unequal, right? What we've got to do is have a boom to get Greece and Ireland and parts of Spain back to something near to what they were at in 2007. But having that boom means that we're going to have 10 to 15% excess employment in 2020, which to me is unsustainable. Right, so what we're seeing here, to get a more sustainable level where it's not so much higher, we're still going to have problems in many regions in the periphery of Europe. Right, and I can't see I can't see that being a policy of allowing the economies to boom at the pre-crisis rate like that, but it's going to be a more sustainable, slower rate of growth. And actually, what we see EU economies generally is like the UK economy writ large. We get the same thing in the UK. Like the South is inflation prone and doesn't need a boom, but there's a demand deficit in the North and in the industrial areas, and a lot of the political problems in the UK revolve around the role of austerity. Whether austerity is good or bad, it depends where you live. I guess it's the same thing in Europe. The older industrial areas, industrial cities of the north of England and Scotland, they're anti-austerity because they need extra demand. And the southeast is inflation prone, and you know, prices are really high, housing and labour is really expensive, and therefore, you know, they don't want a boom to take place. They've already got a boom. So the simulations based on these alternative growth scenarios highlight the dilemma for the EU, especially the Eurozone. Is it possible to impose coordinated centralised policies given the diversity of outcomes, especially between core and periphery? And the problem is, because of the connectivity between regions, what happens in one region impacts on the outcomes in other regions. So isolated policies tailored to individual regions will only be partially effective, because these spillover effects are happening. If you affect one region, it affects another region. And it's not just the neighbouring region. We say it's based on trade. This is what the model is saying. Trade is our connectivity matrix is a trade-based one. So to conclude then, the paper has taken a critical view of spatial econometrics, though not too critical because I'm a practitioner of econometric modelling and I'm aware of both the limitations and the benefits. The Achilles heel of spatial econometrics remains a definition and structure of the matrices that govern interaction between regions. In many examples, these problems are swept aside as of no consequence, but it remains true that what is assumed does make a difference. Attempts to come to terms with this, I've attempted to come to terms with this by providing a basis for interaction between regions based on imputed interregional trade flows. Spatial econometric models are ad hoc, it's said, so we've attempted to justify the presence of the spatial and temporal spillovers in the model. Spatial econometric models are biased because of omitted variables. I've tried to pick up the effects of omitted variables via the dynamic spatial panel modelling, control for unobservable regional heterogeneity by the panel approach, and included a spatial error process to moderate the spatial lag. Spatial econometric models do not reveal true causal effects. I've assumed that the drivers of employment are endogenous, and I've accounted for spillovers in interpreting the impacts of changes in output and capital stock by the prediction equation. And finally, just to finish in my last slide, I'd like to again quote Hashim Pesseron, who says, "Econometric models are important tools for forecasting and policy analysis. It's unlikely that they will be discarded in the future. The challenge is to recognise their limitations and to work towards turning them into more reliable and effective tools. There seem to be no viable alternatives." Thank you.
Thank you very much, Bernard, for this wonderful review, for providing us the main advances in spatial econometrics, especially dealing with dynamic spatial panel modeling, and especially at the beginning of your presentation for remembering some, let's say, critiques on the spatial econometrics. And I picked up one which I feel extremely important, especially for young scholars. That is to say, to apply spatial econometrics as a mechanical fashion. This is, I think, something which is extremely risky. And you raised very well the point that behind a spatial metrics, there must be a theory or let's say, a reason for inserting a matrix, and not only because it's a fashionable point. So I think that this is something that is very, very well taken. I open the floor for discussion because we are nearly running out of time. Please, if someone has some questions, please, Stefano.
One good news. It seems that there are now data for interregional flows. Mark Thyssen and Frank Van Oort have estimated interregional flows for 3 periods, 2000, 2005, 2010.
Okay.
On the EU.
They exist?
They exist.
Okay, that's
So
good news. That is,
data,
yeah, that's good news.
Yes.
Must look at it.
Well, okay.
They're not really available. They are on the internet, but they are
Yeah.
not available. They can be
Yeah.
downloaded.
Okay.
One question. Okay. One question about your connectivity variable, connectivity matrix.
Okay.
I mean, my point is that the problem may be that your connectivity variable matrix is endogenous. Obviously, as you know, we've been using also endogenous matrices. But I just want to know your point of view. And the other question is about the fact that this matrix keeps on changing along time.
Yes.
So you should.
Yeah.
I don't know. How
I agree. That's a limit. Yeah. Actually, it's not endogenous because it's year 2000, so it's prior to the estimation period. But also, it's also based on actually distance, and employment distance is obviously exogenous, and employment in 2000 is like exogenous because it's preceding. But yeah, I think the important point also you made is that it's a dynamic phenomenon, and how to handle a dynamic phenomenon. I think actually, you know, it's only an issue for estimation. The fact that you're assuming that the W matrix is static over time. But when it comes to simulation, you can actually dynamize it, because you can then say, well, actually, let's make assumptions about the evolution of the connectivity matrix through time as well. I haven't done it, but you know, that would be very feasible, I think, and interesting to actually simulate using, you know, some kind of dynamic W matrix. Definitely possible. Yeah.
Thank you. Other questions, please?
I find your speech very interesting.
Oh, thank you.
It was very outstanding some points in it. Basically, would like to know your opinion about the possibility to extend this model with multi-level model.
Wow.
I know you are a leader because you know regions are clustered in states.
Yes. Yeah.
And you have 27 groups
Yeah.
in the second level. So, what is your opinion about the possibility to extend dynamic spatial econometrics to more?
Yeah. I'd have to, I think that's definitely a way forward in doing that, and I think that's for the future. That would be very interesting. But we've not actually done it yet, and I'd have to wait for my theoretically minded colleagues, Buddy and Alan, to work it out, I guess, what the estimator would be. So I'd be interested in applying it, you know. But yeah, I think that would be certainly a valuable development. Okay, thank you.
Other questions? Andrea?
The question would touch upon your presentation and Roberta's remark regarding the exogeneity versus endogeneity of the connectivity metrics. Would you believe that the use of some kind of connectivity metrics that brings in some ideas about sort of social institutional features of the interregional relationships that enhance, for instance, in your case, the growth of volume and so on and so forth, and add some information to the purely geographical metrics, would bias the estimates, or would, let's say, make the estimates not trustworthy or feasible, or can we apply some sort of connectivity metrics that is not purely geographical?
Absolutely, certainly, we could apply a connectivity matrix that's not geographical, and I would hope that other branches of economics involved in, say, kind of network analysis, where it's not spatial, essentially, but it still involves a connectivity matrix, perhaps of ones and zeros, where, you know, point I and point J are connected, but in a non-spatial sense, they're just close together in some way. In fact, in time series, you could write down that equation with the equivalent of a W matrix. It's got its own matrix. Actually, the matrix of time series is not the leading diagonal, the off diagonal of ones, and that so, you know, connectivity either where they're the ones that are closest in time. The extension in space is that the ones and zeros, if you're just using a very simple connectivity matrix, are closest in space. But it could be closeness on any dimension, you know, and it extends way beyond spatial econometrics, I think. People need to kind of, I think, look at spatial econometrics literature and develop it in other directions where it could be applied there. The other point about institutions and a more sophisticated approach to, yeah, I think that's actually valuable because, you know, I've got a very crude, simple model of trade, and you could perhaps have a more extensive model of trade where you've built in all these extra variables as well, and use that to simulate interregional trade. But actually we're told that we don't need to do that anyway. There are data available on interregional trade that could be far better than this set I've got here. But yeah, thank you.
Thank you. Guido.
Yes, thank you. Yes, I have another question about the choice of the matrix. My question is possible to assume that the choice of W is independent from the choice of the model? In the sense that if you choose a matrix that is a connectivity matrix, probably you have quite a sparse RAID matrix. On the other side, if you choose probably a matrix with interflows, you have very full matrix.
Yes.
So this should be some effect on the choice of the model between a spatial line model or spatial error model. So how you can choose together the two?
Yeah, that's an issue. Obviously, the results depend on the connectivity matrix. You assume, and it's going to be effectively a theoretical assumption as to what you think the connectivity is. And you have to go back to what's the connectivity between two remote regions? Well, it's not that they're close to each other. It's that perhaps there's a big trade flow between them. So I think theory should determine, you know, what it is. The other way forward may be to, you know, if you're not satisfied with that, you could perhaps look at how robust the estimates are to varying the parameters. Say you've got a connectivity matrix that's basically sized to the power alpha over distance to the power beta. You can and change alpha and beta to get different connectivity matrices, and look at how the results change according to different assumptions about alpha and beta to see how robust the model is to different connectivity matrices. I don't really prefer. That's possible, but you get a lot of results coming at you from that, and probably not satisfactory ones either. So I'd prefer it if you could actually justify your connectivity matrix on some theoretical rationale, which has to be testable, I agree. You know, and often it isn't easily testable, but you know, otherwise you're into large amounts of estimation to check the robustness. And maybe it doesn't matter, maybe, you know, the results will. But here, what happened was when I assumed endogeneity for my x's, that actually increased the parameter on the spatial lag. So, I mean, that meant that the spillover effect in the model was very great, which is why in that short and long run effects they were quite big, because the spillover effect was very large. So, actually, there are two things going on there. What you assume about the regressors, either endogenous, exogenous, or predetermined, and also what you assume about the connectivity matrix. They're not separate because they both impinge on the result you get. But yeah, it's a big issue, but you know, there are other ways of. There's another literature out there that doesn't rely on W. I must admit that I think if you go back to Luke Anselin's book in 1988, he talks about spatial SUR models where you estimate the residual correlation from if you've got time series, get the residual correlation from that, and that gives you a measure of the connectivity between the residuals. So there is that literature out there, but most of them rely on long panels to get reasonable estimates of the correlation, and then that's only the residuals. It's not necessarily the endogenous variable. So you might just solve the problem as to what the correlation in the residuals should be. But most of the competitors out there rely on very long time series or longer time series. And here, the problem is once the regions get smaller, the shorter the time series, because you get changes in definitions of variables, boundary changes, and so on. So, you know, once we start narrowing it down to nuts 2, nuts 3, then the available data becomes rather short in terms of panel, and therefore it's not possible to do much there. So, I hope that answers it.
Thank you. Other questions? No? Then we thank Bernard very much.
Thank you.
I'd like to say that differently from Ron Boschma, Bernard provided us with a paper on what is said. So this paper will be published in the Italian Journal of Regional Science, so you can read about what was said today. So thank you very much, Bernard, for being here, for the paper, for your presentation, and hope you will enjoy your stay in Italy. Thank you very much.
Thank you very much, Roberto. Thank you. Thank you.